Hi, welcome to the third part of the probabilistic programming session on message passing and factor graphs. We're looking at a situation where a company wants to hire an applicant and they want to determine the applicant's skill level. In the first part, we asked the applicant questions that they could get right or wrong, and we tackled that with a Bernoulli likelihood and a beta prior. In the second part, we asked them questions that they could get a score on, so a score of 0, 1, or 2. And we tackled that with a categorical likelihood and a Dirichlet prior. In this third part, we are going to rate the applicant. So imagine a situation where an interviewer and an applicant have a conversation, and then later on the interviewer marks a score, a rating for the applicant on this line here. So in principle, this is real valued because you could be anywhere on that line, and then of course later on when you encode this into a computer, it will be discretized in some way. But in principle, this is a real valued response. So we are going to model these outcomes, these ratings, for each question with a Gaussian distribution. So we denote this as a normal of the current response variable x, and then we have a mean theta and some, in this case, known sigma. So the general model is the same before, as in where we just swap distributions again. So in this case, for the first question, the mean is unknown and the variance is 10. And for the second question, it's the same, but we have a higher variance of 15. So the second question is a worse indicator of skill level than the first question. So we picked a prior of so the prior for the Gaussian likelihoods mean. Conjugate prior for the Gaussian likelihoods mean is another Gaussian distribution. So the prior P of theta is Gaussian distributed with its own mean of 60 and the variance of 20, which describes our prior beliefs about applicants coming to the interview. So if we encode these distributions into this factor graph, the syntax looks exactly the same as before, and we're just swapping distributions again. So the prior theta is a Gaussian parameterized with mean and variance, with a mean 60 and variance 20. And each of the likelihoods is also a Gaussian parameterized with mean and variance, and then the unknown theta, and then variance of 10 and 15. This produces the same graph, the same generated graph, where again the only difference is the specification of the distributions. Again, the same message passing schedule, and if we have a closer look at these messages, so again in this data structure we input the applicant's scores. So imagine something like 61.5 and 72 out of a possible 0 to 100. The first message is quite clear, that is the prior with a mean of 60 and variance of 20. The second message has a mean of 61.5, which just happens to be that actual observed outcome, and then a variance of 10, which is something that we clamped earlier. Same is true for the third message. The fourth message, as Formulab reports it, is a bit unusual in that there is not an M here, but a xi, which stands for chi. If you've watched Bert's lecture on Gaussian distributions, then you'll remember that when you take the product of two Gaussian density functions, PDFs, not the product of two Gaussian variables, if you take the product of two Gaussian PDFs, then you are weighing each of the means with their precisions, you're summing that, and then you're renormalizing that. So what you see here is an alternative parameterization of the Gaussian, where this chi is just the sum of precision weighted means. And we can request the mean of this distribution, and Formulab will automatically renormalize that, or we'll rescale that and report the appropriate mean. And that's what we did here, and you can see that the mean is 65.7, and you can see that it lies in between the observed outcome 61.5 and observed outcome 72. Note that the new variance of this product of those two messages is a lot lower than either of the two constituent variances, so 10 and 15. which indicates that the information from asking 2 questions is always, or is going to be more informative than just asking one of the questions. So if you visualize this process, this black one is the Gaussian centered at 61.5. That's this one with the variance of 10, and the second one is at 72 with the variance of 15. You can see this is wider, and the message 4 that's been renormalized, that's the weighted average of both constituent PDFs, and the balance is more towards message 2, because message 2 is sharper, is more informative, it's less variance. If we then move on to the visualization of the message from the prior and the message from the equality node, so the message that comprises the information of both likelihoods, then we can see that because the prior is actually quite uncertain, it's quite wide, it does not have as much influence on the resulting marginal as this message from the equality node of the observations, based on the observations. Yes, so this is really a weighted average of those two. So if you are unfamiliar with what is happening here with these Gaussian PDFs, I suggest you have another look at Bert's lecture on the Gaussian distribution. Outside of that, I strongly encourage you to play around with these parameters. So there's been a few values that have been completely arbitrary, such as these ratings, or the variances in each of the likelihoods, or the prior parameters. So the whole point of the probabilistic programming sessions is that not only that we go a bit more into depth into example, but also you get a chance to play around with these things, to develop an intuition for distributions, parameters, products of distributions, how all of these things affect your estimate of something, so in this case skill level. Again, I strongly recommend you play around with this a bit. And that concludes this second probabilistic programming session. On the next session, we'll be looking at regression and classification, which I think will be a lot of fun. And yeah, hope to see you there. Bye.